Okay, we're going to continue on here, do a little potpourri of some chapters, but we're basically chapter 6 here, and we're going to talk about reactions, balancing equations, and types of reactions. So let's get into it. Obviously, a process where one or more substances change into another substance or substances is a chemical reaction. It's a chemical change. Obviously, one way that we represent a chemical reaction is using a chemical equation. And in a chemical equation, obviously, we have on our left-hand side of the arrow our reactants, which are starting materials, and they go to products, which is our stuff that is formed. So here we have 2 molecules of H2 plus a molecule of O2 makes 2 H2Os. And other things that we sometimes will see in an equation, and if we do have it sort of balanced here, is we can look at the coefficients as we do in stoichiometry. And again, we could say that those are the atoms of magnesium reacting with 1 molecule of O2. Makes 2 formula units of magnesium oxide. Sometimes with ionic compounds, they're referred to as formula units. We could also use the mole-mole relationship like we'll do in stoichiometry, which is, again, also the coefficients. 2 moles of magnesium react with 1 mole of oxygen to form 2 moles of magnesium oxide. Conservation of mass here, right? Got the same number of elements on each side, which means they have the same molar masses on each side, and they will add up to the same amount of products. These are not a gram to gram relationship or anything like that. Other things that we commonly will see in equations is we'll see the states of things. So solid, liquid, gas are aqueous, which is a solution or a water environment. Sometimes we will see up on top of the arrows a little delta symbol that usually means heat. We will also sometimes see a catalyst written up on top. That could be something like platinum or like H plus. A catalyst is not a reactant. It's not a product. It does not get used up in the reaction. So a catalyst, not a reactant, not a product, and does not get used up in the reaction. It is there simply in most cases to allow the reaction to occur faster. So it will allow it to occur faster without getting used up in the process. And we'll talk a little bit about catalysts in the last chapter that we talked about this semester. But catalysts essentially find an alternative pathway, a more efficient pathway for that reaction to take place, and thus usually speeds up a reaction. Now, when we balance the equation, it's really important, for example, if we have an equation such as this, and we are given, for example, the equation in words, it's really important to make sure that you start out with the right formulas first and then balance. And you want to always do it in that order. Make sure you have the right formulas and then balance. You do not want to do it together. And that is usually a problem for a lot of people, especially if they have the reactants and they need to predict the products. Yeah. So if they don't really have what's on the product side, a lot of times they try to write the formula and balance the equation at the same time, and they end up with incorrect formulas and the thing will never balance. So you want to always kind of do it in that order. Forget about the balancing part of it. You want to make sure that you have all of the right formulas down and then go back and balance. When we balance an equation, again, we only change the coefficients, so only the numbers that come in front. We never change any of the subscripts or the numbers that are on the bottom. Otherwise, we will be in trouble. And when you balance the equation, there's a couple of sort of rules that you want to make sure that you follow. And the two main rules are that when it is all said and done, your equation should have all whole numbers for the coefficients. So these coefficients in front should be all whole numbers, and they need to be the simplest set of whole numbers. So they need to be all whole numbers and the simplest set of whole numbers. So what do I mean by that? For example, if you balance the equation, 2a plus 4b goes to 6c. Even though it may be balanced, you technically go through and divide everybody by 2 and still get whole numbers, and you should do that. And this would be, in this bad example here, that would be the properly balanced equation. So you always want to make sure that it's the simplest whole numbers when you balance it. There are a lot of different sort of methods to balancing equations. Most people just try a trial and error type method. But you kind of want to do what is maybe easiest to balance, maybe leave a lot of complicated stuff for the end to fix it. So for example, here, if we were looking at this one, I would recommend maybe making a table. You have your reactant side, you have your product side, and you have your elements that are present. And here we have 2 carbons on the left. We have 1 carbon on the right. On the left, we have 6 hydrogens, 2 hydrogens on the right, 2 oxygens on the left, and we have 2 oxygens here plus 1 more over here, which actually gives us 3 oxygens total on the right-hand side. Remember, the goal here is conservation of mass in a chemical reaction. We don't lose any elements along the way. All we do is break bonds and make bonds, so everybody should still be there that we started with. In this case, I personally was just going to start with what seems easy, and that seems the carbon seems easy here. I could just put, again, a 2 in front of it. When you do put a coefficient, it goes for everybody that's behind it. So that would give me 2 carbons. Still have 2 hydrogens. We now got 4 oxygens there, plus 1 more there, makes 5. At this point, I have a choice of hydrogen or oxygen to sort of go after. I am actually going to choose hydrogen. The reason I'm going to choose hydrogen is hydrogen is only in one thing on each side. Makes it a little bit simpler. Oxygen's in a couple of things on the right-hand side and one thing on the left-hand side. So I'm going to save that for the end. And at this point, I could balance it by putting a 3 in front of my water. Again, that goes for everybody behind it. That's going to give me 2 carbons. We got 3 times 2 is 6 hydrogens. We have still 4 in the front. We now have 3 times 1, which is 3. This now gives us 7 oxygens in this particular case. At this point, we need to basically balance the oxygen on the left-hand side. And we definitely don't want to kind of mess with the numbers on the right-hand side because we're almost there. So we basically need to turn our 2 into a 7. And as you may remember, or if you don't remember, you can do that maybe with something like 7 over 2 in this case. Because if I take 7 over 2 and I times it by 2, I end up with 7. And in this case here, I will now have 2 carbons, 6 hydrogens, and 7 oxygens. And this is now a balanced equation, but is it a correctly balanced equation? It is not, because all of them need to be whole numbers. So this illustrates a really good point that you can balance an equation with a fraction, and sometimes that occurs. And if you do, you just need to get rid of the fraction. So to get rid of the fraction, we need to multiply the entire equation by the denominator, and that would give us 2C2H6 plus 7O2 goes to 4CO2 plus 6H2O. And this, if I did not screw up, should now be a balanced equation. We now have 4 carbons on the left. We got 12 hydrogens there on the left, and 7 times 2 is 14 oxygens. On the right, we got 4 carbons. 4 times 2 is 8, plus 6 more is 14 oxygens. And 6 times 2 is 12, so we are balanced. So again, sometimes you do need to use a fraction to balance the equation. You just need to clear it when it's all said and done. Any questions on that there? All right. So So scroll through that. That's basically what we just did. Okay, let's take a look again. If we make a table here, reactants, products, we got nitrogen, oxygen, hydrogen. We have one nitrogen on the left, two on the right. We have one oxygen on the left and one on the right. Two hydrogens on the left and two on the right. So everything looks balanced except for nitrogen. Seems like a good place to start. So we'll go with two. Again, going to go to everybody behind it. Two nitrogens, two oxygens, and two hydrogens. And that commonly happens, kind of mess something up when you balance something. Looking at our table, oxygen seems like the next place to go to on the right-hand side. So we'll put a 2 there. That gives me 2 nitrogens, 4 hydrogens, and 2 oxygens. So now we're really close. All I have to do is go back to the left here and put a 2 there. And we got 2 nitrogens, 2 oxygens, and 4 hydrogens. And we are balanced. Any questions on that one there? All right, so let's take a look. Reactants, products. We got carbon, hydrogen, oxygen. This one here, so 3 carbons. That's the one we just did at the beginning. I feel like it seems very similar. Was that one? What was that one that we did? No, C2H6. All right, felt very similar. All right, so we got 3 carbons on the left there, 1 on the right, 8 hydrogens on the left, and 2 on the right, 2 oxygens on the left, and again we got 2 there and 1 more there makes 3. So again here I'm just going to start with what seems simple to me. Carbon seems simple, so I'm just going to put a 3 there. That will now give me 3 carbons. Still have 2 hydrogens. We now have 6 oxygens there, plus 1 more gives me 7. Once again, at this point, I'm between hydrogen and oxygen. I'm going to choose hydrogen again because it is by itself on each side. Oxygen's in multiple things. So we're going to go with 4 there to our hydrogen. That will give us 3 carbons, 8 hydrogens, 6 oxygens in the first one, and now 4 in the second, which gives us 10. And that makes it pretty simple. We come back this way, put our 5 there. 3 carbons, 8 hydrogens, and 5 times 2 is 10 oxygens in this case. Any questions on that one? All right, let's try a few more here just to make sure. All right, write the balanced equation. For this one, diboron trioxide reacts with water to form boric acids and balance it. See what you come up with. All right, let's take a look. So diboron trioxide, that's definitely type 3. So prefixes mean B2O3. Reacts with water, which we hopefully know is H2O, to form boric acid, which is BOH3 in this case. Again, I'm not concerned about the balancing part here. You want to, again, get the correct formulas down. Now you should be concerned about the balancing. So let's take a look at that. And in this case, we got 3 elements. We got boron, oxygen, hydrogen. So we have 2 borons on the left, 1 on the right. We got 3 oxygens there, plus 1 more makes 4. This 3 does get distributed to everybody inside. So we got 3 oxygens there on the right. And hydrogen, we got 2 on the left, and again, the 3 that gets distributed. Not much to work with on this one, so boron seems like the easy move, so we'll go with a 2. That 2 also gets distributed to everybody that's behind it, so that will give me 2 borons, basically 3 times 1 for the oxygen, times 2 is 6, and same thing for the hydrogen, 3 times 1 times 2 is 6, so it kind of has to multiply in and then multiply out there to the 2. That then brings us to oxygen and hydrogen that is not balanced on the left-hand side. Once again, here I'm going to tackle the hydrogen first as it's in only one thing, as opposed to the oxygen that's in multiple things. So this seems like an easier move. And to get my hydrogen to 6, I just need to put a 3 in front of it, which obviously goes to everybody behind it. That gives me 2 borons. Oxygens, I got 3 there and 3 more over here. So that actually is a 6, and that takes care of that guy. And then 3 times 2 is 6. So here, by just fixing the hydrogen, it also fixed the oxygen. So again, as you can see, if you got multiple sort of elements, same element in different things on one side, you may want to kind of save it for the end and kind of just take care of everything up to that point. Any questions on that one there? All right, a few more here to finish it out with here on our balancing. Let's balance up this guy. Okay, so counting up everything we got going on, we got 1 nitrogen on the left, 1 on the right. We got 3 hydrogens on the left and 2 on the right. 2 oxygens on the left, 1 oxygen there, and 1 there is 2. In this case, everything but the hydrogen is balanced. We need to actually put a coefficient on both sides here to start with. Common number for hydrogen there is 6, just by multiplying those 2 numbers together, 3 and 2. So to get this hydrogen to a 6, I need a 3, and to get this one to a 6, I need a 2. That's going to give me 2 nitrogens on the left. 3 times 2 is 6 hydrogens and 2 oxygens. On the right-hand side, 1 nitrogen, 6 hydrogens, and we have 1 oxygen there, and we got 3 more there, so that is 4. So we fixed the hydrogen, kind of screwed up everything else. Once again, here at this point, I'm going to shoot at the nitrogen, as again, oxygens and a lot of things on the right-hand side. So nitrogen seems the easiest to just fix, so we can put a 2. That will give me 2 nitrogens, still the 6 hydrogens. We are now up to 2 there and 3 there, which is 5. So at this point, we clearly don't want to erase any digits here. So we only have the oxygen to deal with on the left. And we again need to make basically our 2 into a 5. So this is another situation where a fraction would be helpful. If you're not sure how to choose the fraction, it's pretty straightforward. The number that goes up on top is the number you need, so I need 5. And the number on the bottom should match that guy right there, so that should match. And that's the number you need. And if I do that, I now will have 2 nitrogens, 6 hydrogens. And again, when I take 5 halves times 2, I end up with 5 oxygens. So here we are balanced, but we do need to clear it. We cannot leave it with a fraction or a decimal or anything like that. So we got to multiply everybody by 2, which is the denominator. And that will give me 4NH3 plus 5O2 goes to 4NO plus 6H2O in this case here. And again, we should still be balanced. We got 4 nitrogens on each side, 12 hydrogens, 6 times 2 is 12, and 10 oxygens, 4 oxygens there, and 6 more is 10, and we're still balanced at this point. Any questions on that there? All right, a couple more here, just to finish up for today. Balance these guys up, see what you end up. Okay, let's take a look at these. So on these here, we do see some polyatomic ions in each of these equations. And unlike the previous ones that we balanced where you sort of made a table and went sort of element by element, sometimes it's easier if you do have polyatomic ions, like we have phosphate here, and we got carbonate here and carbonate here, is to just sort of balance them as whole units rather than element by element. There's a lot less sort of multiplying in and sort of chance for error. So if I was to do this, I personally would look here and go, okay, well, you could really start with either polyatomic ion. I'm going to start with phosphate because carbonate on each side is the same. We only have 1 on each. Over here, we have basically 2 phosphates and only 1 phosphate here. So to fix that, I'm just going to put a 2 in front of my phosphate on the right-hand side. Now, when I do this sort of method, where I want to go next is actually whatever else is attached to that phosphate on this side. because obviously when I put the 2 there, it's going to mess up the sodium. So now sodium has 6, and that's where I should go next. I'm just going to go to the left-hand side to sodium. Sodium has 2, so I'm going to put a 3 there to give it a 6. And now at this point, where I would go next is whatever's attached to sodium, because obviously that 2 is going to affect the carbonate in this case. And now I have 2 carbonates, so I would go to the right-hand side and put a 2 there. That gives me my 2 carbonates, also gives me my 2 iron. So I come over here and I think I did some bad math there. That's a 3 I need there. There we go. Since that's a 3 there. That gives me 3 carbonates on the left and 3 carbonates on the right there. And that gives me 3 iron on the right, which is exactly what I need there on the left. So this will usually fall into place if you put the right number there. It will fall into place, usually everything at the end there. So a lot of times it's a lot easier to just kind of keep those polyatomic ions as kind of units and balance them that way. I would take the same approach down here. I see a sulfate on each side. I also see a hydroxide on each side. Now, it doesn't matter which one you start with. One may work better than the other. So here I will start with the sulfate. And at that point, I got 3 sulfates on the left or right-hand side, 1 on the right. So I'm going to put a 3 there. That then will affect the silver, which means I now have 6 silvers. So I'll go to the left right-hand side and put a 6. That gives me my 6 silvers I need, gives me my 6 hydroxides, which means I do need a 2 here to give me my 6 hydroxides, my 2 chromiums, which is exactly what I need. So it's usually a much faster way of balancing these type of equations if you have polyatomic ions in it. Now look, if you kind of chose maybe the wrong polyatomic ion, like in this case, you chose to start with the hydroxide. So if you chose to start with hydroxide, you would put a 3 here because there's 3 here. And that will give you 3 silver, which clearly if you come over here, you got a 2. That's not so great. But you can fix it pretty simply by going 3 times 2 is 6. So really I need 6 silvers there. Erase that, put the 6 there, and then you could actually continue on and fix it pretty quickly. Or you could just go back and start with the sulfate and go that way as well. So that's another alternative way that you could do it. But even if you kind of hit the wrong polyatomic ion, you can sort of correct yourself or just go back and start with the other polyatomic ion in that case. Any questions on balancing equations? All right, we'll lay that up.